All right, so now that we've taken a look at velocity and what velocity can do for us and coming up with a motion diagram, we're going to go one step further. And before I actually go that one step further, I want to make a point. Some of you have had, a lot of you have had physics, and you've talked about speed instead of velocity. And again, the difference between speed and velocity. Speed is the absolute value of velocity. Speed doesn't tell you what direction you're going in. Just tells you how fast you're going. Velocity tells you how fast you're going and in what direction you're going. So in calculus, we use velocity. But know that whenever, if a question might be talking about speed, that's what it's asking for. It's asking for the absolute value of velocity. So you might want to make a note of that, is that speed equals the absolute value of velocity. Okay? All right, so now let's get into acceleration. Going back to that car example, I said something about in the beginning. If I'm going from home to school, my displacement, I think I said, was 5 miles. Okay? If I'm traveling at an average rate of speed of 35 miles an hour. Okay? So that would be my velocity. But there are times, where I can't just pull out of my driveway and be at 35 miles an hour and pull into the school parking lot and be at 35 miles an hour. There's traffic lights in between. So there's hills, there's speed limits that are larger than 35 miles an hour. So when I change my velocity or I change my speed, that is considered an acceleration. And if your acceleration is positive, it means you're speeding up. If your acceleration is negative, it means you're slowing down. Okay, so basically, whenever you step on the gas pedal or step on the brake, you're changing your acceleration. Okay, and the relationship here, I've done this cover up here, and you can see it in your book as well, because I feel like doing the limit notation would just be a little confusing. Okay, but you can see that's where we started with finding the derivative, and it was the idea that the derivative is the slope as the change between the 2 points gets to 0. So as the change here is heading towards 0, closer and closer together, those points. All right, so it's just dealing with the derivatives. So in order for us to calculate velocity, what we did, or come up with an equation for velocity, was we took a derivative of displacement. Because acceleration is change in velocity, the way we'll come up with our acceleration function is to find the derivative of velocity. Well, if velocity is already the derivative of displacement, then that implies that acceleration is the second derivative of displacement. So I'll be writing those relationships a lot, because that's how I usually start my equations, is by writing that, so that my grader can see that I know, in fact, what I'm doing. Even if I screw up something as simple as the power rule, at least I'll get the rationale or the reasoning points for it. So we're going to start like we started with velocity, and we're just going to look at the average acceleration. And average acceleration is just finding the slope between 2 points of the velocity. Okay, because slope is your change. So I just want to share one thing that Desmond shared with me on Tuesday, and that was that he had an aha moment that derivative is not actually the slope, it's the equation of all of the slopes that could happen. And without having you guys in class, I don't get to experience those aha moments. So anytime you have something like that, please make sure you share it with me, because that will help me figure out where you guys are. One of the reasons we take this course at the pace we do is so that we have a good background in it. So anyway, average acceleration is going to be the change in our velocity from time of 1 to time of 4. So what that means is we're just going to apply the slope formula here to the velocity formula to find out what our average acceleration is. So for part A, I have to find out what the velocity is when the time is 1. Okay, so I'm going to do 6, 1 squared minus 42 times 1 plus 60, and type that all in my calculator, and I end up getting a velocity when time is 1 of 24. So just as a review, a velocity of 24 would tell me that I'm moving to the right on my motion diagram because it's positive. Okay, so one of my points is going to be 1:24. And then I need to find the velocity when time is 4. So I'm going to do 4. I'm sorry, that's supposed to be a 6. All right, so 6 times 4 squared. I don't know why that changed colors. I don't like that. Let's try this again. We'll go to the pen and we'll take it back to black. There we go. 6 times 4 squared minus 42 times 4 plus 60 typed in my calculator gives me a velocity of -12. And a negative velocity means that my motion diagram would be moving to the left. So my second point here is 4, -12, and to find the average acceleration, which we'll use as A. Okay, the average acceleration is going to be -12 minus 24 over 4 minus 1. So that gets me -36 over 3 or -12. And the units for displacement is meters, the units for velocity is meters per second, and the unit for acceleration is meters per second squared. And you can, some of you like to write that with that negative exponent, that's fine as well. So this is meters per second squared. So that's our average acceleration between those 2 points. And now what I want to do is I want to find the instantaneous acceleration. So in order to find the instantaneous acceleration, I'm actually going to go through and I say the acceleration at time t is equal to the first derivative of the velocity. So I'm going to find the first derivative of velocity, and that will get me 12t minus 42. And then if I'm looking for instantaneous acceleration, I'm going to substitute in the time they give me, which is 3. So that's going to be 12 times 3 plus, minus 42. Minus 42. And again, it switched to green. Why does it switch to green when I do that? Minus 42. All right. So that ends up getting us an instantaneous acceleration of -6 meters per second squared. Okay, so back when we were doing the original information and we were trying to head down to one specific number, we saw these be much closer. And that we just kept reaching a limit, basically. We just kept getting closer and closer and closer the closer we brought those x values together. When we're talking about acceleration and velocity and displacement, sometimes it even changes direction on us, and we didn't realize it. Because you can see this at one point was moving to the right, and the next point it was moving to the left. So that could cause us to see something drastically different in between the average and the instantaneous.